So the topic here is not mining, it's construction. My colleagues, Dr. Anders Carlson, Neil Lynch, and Madhu Tangavello are in architecture, actually, with Madhu having joint appointment in the astronautics department. The really prerequisite for any kind of serious operations on other planets is to have some form of infrastructure. If you want to use an analogy, think about the early expeditions to like Arctic or Alaska. We had a single engine airplane landing on snow. And this is pretty much what we've been doing on Moon, for example. We have landed there, people 6 times. But these are small landers, and really we haven't built anything there. We just have placed a flag there. If you want to do, for example, mining, you're going to have huge landers going there. You are going to need a landing pad. You cannot have these landers land on soft sand. As I understand, the last lander that landed on Moon almost tipped over because it landed on a slant surface. Then you'll need roads. Your settlement has to be protected from the projectile from the exhaust plume of the landers, so you need blast walls. You need hangars to protect your landers and other equipment from radiation and micrometeorites. And you need shade walls. You know about the temperature on the Moon is pretty serious under direct sunlight. So these are just the very basic infrastructure stuff that we propose to NASA. Innovative Advanced Concept Program, and fortunately we won the award and we are in the 2nd phase of it. We are working closely with the Kennedy Space Center. They are really great source of knowledge on the planetary materials. We have had some interactions also with JPL and Ames, and with NASA Marshall Space Flight Center on radiation shielding. So pretty much all the conceptions about human settlement there, as you've seen in a lot of imaginary pictures, are based on taking components, prefab, inflatable, and other alternatives from Earth and assembling them there. But if you consider that taking 1 kilogram from here to the Moon will cost you over $100,000, then you'll notice that you really cannot do much with this kind of approach. So you really have to base everything on the use of whatever is there. And this was the principle behind the proposal that I made to NASA. And it was based on a technology that I developed a few years back called contour crafting. So I've been active in fabrication technologies. I've developed several 3D printing methods for different materials, polymers, metals, ceramics. But as you know, all of these processes are pretty slow because they use very thin layers. If they increase the layer thickness, there will be 2 problems. One is that physically, these processes cannot handle them. For example, laser-based processes. The laser cannot penetrate powder very deeply and controllably. And the second problem is that even if you can process these layers, thick layers, you'll have staircasing effect on slant and curved surfaces. So the principle behind contour crafting is pretty straightforward. We use paste material and we extrude it. As the material comes out, we constrained by a trowel, the angle of which is controlled by computer, and then the whole thing is robotically moved in 3D space. So you can see here that different kinds of surfaces have been produced with pretty thick layers and yet great surface quality. These are some of the ceramic parts that we have produced. By using proper algorithms, you can even create very sharp corners. Now, the speed of fabrication here is extremely fast compared to regular 3D printing. So we did a number of experiments here. This is a hybrid method. For example, the external material in here is plaster, and the core is concrete. And we finally managed to extrude concrete itself with nearly zero slump and large aggregates. Because the orifice of contour crafting is big, it allows you to build stuff with large aggregates. And it hasn't been very easy, so don't assume that we just put concrete there and it worked. You can try putting some concrete in just a 1 foot, 1 inch tube and try to press it in by your thumb. You will see that it won't go. There's a bridging phenomenon that happens, and it just gets stuck, clogged. And if you put a pumping concrete, all the juices go through and all the sand stays behind and it clogs. So concrete is very hard to pump. And the big concrete pumps that you see use usually very big tube or hose, and they're using very runny concrete. Not the kind of viscous concrete that we use. So we have added a lot of features to the technology. This is doing automatic reinforcement using steel coil. Or this could be nichrome wires for heating. We have been playing with sensors. That's the brown one is conductive concrete that has got graphite in it. We can automatically power sensors without needing to wire them. These are wireless sensors. This is one of the machines that we've built. This is all pretty light, about 500 pounds, 250 kilograms almost. 3 people can easily move this thing around. These are some of the largest structures that have been built. That's probably the largest structure that was built by 3D printing for the first time. As you see, the layers are like 2.5 centimeters. Now we can actually build with much thicker layers and we're still with smooth surfaces. This particular nozzle, as you see, can do the hollow structures with corrugated internal cavity. The strength of this concrete, 10 hours after fabrication, is demonstrated here. You can build actually beams for the roofs, whatever, out of the same concrete. This particular concrete has small fiber reinforcement mixed into it. Well, this was supposed to be a video. Thank you. Yeah, so you can see and compare. If you've seen 3D printing, you can compare. Yeah, how fast this is compared to other technologies that you've seen. This is ceramic, basically, wet clay being deposited. The layer thickness is about 6 millimeters. And as you see, that's a perfectly 3D object.
That real time?
Yes. This is concrete with, again, reasonably large aggregates. As I told you, this is zero slump, so you can build walls without any formwork. You can use curved walls, as I showed you. This is another nozzle that does this thing in 2 pass, building hollow walls out of concrete. Yeah, try.
That's just ridiculous. It's not standard.
This is being built on that same gantry, the picture of which I showed earlier. As you see, there is a curved feature there. This is a full-scale, tall wall. And this one shows how curved specimens can be built. So you can imagine, if you were to build a curved wall like this, using current method, you have to use lumber, forward, and for doubly curved surfaces is almost impossible. You have to really use a CNC or whatever to produce such things. But in here, like this S-curve structure. So this animation shows how this would work in case of like building a house. According to our evaluation, the speed of fabrication would be about, for 1 square meter of the wall, about 3 minutes. So an entire 200 to 300 square meter house can be built in less than a day, in about 20 hours. And custom design on site with all kinds of beautiful architectural, exotic architectural features. So this is the future of construction, and hopefully we'll make it happen soon. So this is the base technology that I proposed to NASA. And of course, now the condition of construction is going to be different there. Getting water on Moon and Mars is difficult. Even if you get it, of course, it's going to evaporate. The concrete that you mix, has to be done under a dome or whatever. We don't want that. So we looked at alternatives. Of course, again, the intention was to not take any additives from Earth, like polymeric binders or whatever. So we looked at the possibilities there. So one possibility is use of sulfur. Sulfur is a great binder, and you can find it on the Moon and more of it on Mars. So if you mix sand and sulfur and heat it and extrude it, basically gives you pretty good concrete. One point quickly I want to bring to your attention is the capability that Freeform Design gives you. This building used to be the house of a carpet merchant, Mr. Bourgerli. It's in the city of Kashan in Iran. It's one of the most earthquake-prone regions there. And this is made only with clay and straw, adobe. And it has stood the test of time. It probably got a lot of little cracks every time there was an earthquake, but it repaired itself whenever it rained. Adobe material self-repairs. So the strength comes from the geometry, right? You can test that with a piece of paper. If I hold this piece of paper, it cannot hold its own weight. But if I curve it a little bit, of course it becomes very, very strong comparatively, right? So if you have this ability to build curved structures, you already gain strength even if you use the same material. Of course, the ingenious patterns that people use actually can result in these vaults and domes and any kind of combination without even scaffolding. But these people are rare today. You cannot easily find them. But you can program these patterns into robots. Like contour crafting nozzle can be moved in space to do that. So going back to the Lunar Martian application, we can use the same kind of patterns. This is supposed to be like a model of a lunar fuel vessel. And as I indicated, these are some of the basic infrastructure elements that we have proposed. Future structures could include human habitats, more sophisticated pressurized systems. Now, regarding landing, this is exaggerated in the z-axis. This is the surface of the moon. And there are certain areas where the lander can actually land. A lot of other areas are not suitable for landing. As you see here, there's a relatively sharp slope. This one shows the trajectory of the lander as it approaches the surface. And future landers are becoming heavier and heavier, as I indicated. Look at the mass of this one. Pretty impressive, and the future ones, as I indicated, are going to be even bigger. So really they need reliable landing paths. So the time does not allow me to go through the details of these, but these are some of the considerations that you have to have. For example, in the landing path design, sulfur concrete will not work because it will simply melt. The temperature is very high, so we have to resort to other methods, which I mentioned here. Infrastructure designs, here is the apron maybe can be built with sulfur concrete. So this is our first conception of how the landing pad would look. That black part is the blast protection wall. This is an artistic image of how it looks. So the high temperature one would be molten concrete, molten regolith, much like flowing volcanic lava. You've seen that if you've gone to Hawaii, the big island, you know this, that it's constantly streaming down, and as it cools down, it turns into a rock. It's porous because there is oxygen and gases here, but on the moon, it's going to be pretty solid and consistent, glass-like. So that's what we like to use, to melt and extrude the soil directly without any binder. So there are ingredients in the lunar regolith. The melting temperature is different, so the lowest ones melt at 1100 C. And the rest will remain solid, and that's great because they'll act like aggregates in concrete. So the low temperature ones act like binder. And so the next one is hangar construction. Again, this is a conceptual design. The robotic system is JPL's athlete robot. We are not attempting to build robots. So that's the contour crafting arm in this particular thing. We use a microwave to melt. We have done some melting using resistive heating, actually kind of successfully. Yeah, well, so these are some structural issues that Dr. Carlson is involved in. He's a structural engineer, actually. Road making is another one that we're looking at. Again, the same kind of concerns that are here with respect to roads would also exist there. Considerations with respect to blast flow. So this is the very first attempt on sulfur-based concrete. So if you take sand and sulfur, this much sulfur, that much sand, you mix it, you get that thing. And if you heat it and extrude it, you'll get that. So, well, this was very primitive first system that we built. As you see, that is, it looks like concrete, it looks like wet concrete, but it's actually sulfur-based. And as you see, it's going to get clogged soon, and it's going to stop. So yeah, it just already got clogged. It's not very easy to do that, although we have all kinds of vibrations and all that. So we have more sophisticated extrusion now. As you see, the top one is Martian regolith, the low one is Lunar regolith. We have built a multi-layer structure with both, as you see. And we have done molten regolith testing and sintered one. The upper one is molten and the lower one is sintered. The characteristic with respect to compressive strength, the Martian regolith simulant actually, is not very good. They say it's not really real. And the recent drilling, which was shown this morning, actually has some sign of hope because the material underneath, it looks much different. It's like ash, whitish material, which is very different than the red material. So these are all experiments with sulfur-based Martian concrete, and we did some testing of those. So there are issues with respect to power. Where do you get all this power when you melt such high temperature stuff? Well, okay, if you can compromise the speed of construction, the rate of construction, you don't have to build it in one day like you do now. So you extrude very slowly, then the power density will be enough to build over a longer period of time. There are different methods of powering things. There are control issues as well as issues of sensors and communication. This fall under the autonomous telerobotics and co-robotics configurations. The choice of robots. One is athlete. There are other NASA robots and rovers that you can use, but this one could be used for road building. There are robots could be used for service and repair and methods of launching them. There are several actually candidate vehicles. And in private sector, SpaceX, as you know, is pretty active. They're very interested in our work, so hopefully we're going to start a project with them as well. So this is our timeline, project timeline for the next 2 years of phase 2 of the NIAC project. So the dual use for this, of course, is very important. We are advancing contour crafting on Earth using hydraulic concrete and other interesting material. But if we succeed here, there are important ramifications. Like we're talking with Dr. Christian Anderson, who, in Hawaii there is a lot of lunar regolith-like materials, volcanic materials, and not much ingredients for making cement. So, and there's also sulfur or other binders that we can use, so this technology could be used there. And in the middle of the desert, if we could melt sand and build the stuff, the world is actually facing shortage of water in a lot of places. So, again, the dual use will be significant. Okay, I guess my time is up. 2 more minutes. Okay, what do you like me to tell you? So let's answer the question.
For terrestrial use and space use, how does the concrete quality give you gas and liquid permeability through there in the case you've got positive pressure of gas or liquid?
I didn't get the question.
Can the walls withstand positive pressures of gas and liquid without being permeable?
Oh, well, we haven't tested that. We didn't need to. Well, one thing that we are looking at is building like water tanks and stuff. But you can always coat those. You can coat the inside of them.
Sulfur.
Make them impermeable.
But it's, the concrete you sealed completely from all fires. Because, if you construct this on the moon or somewhere on Earth, you don't want the oxygen to go out of the building, It should be completely sealed.
Right. So that's the same thing. You've been making it impermeable, right? Well, there are, again, first of all, you can build a structure like a dome and then put an inflatable in there, right? You have a polymeric shield, or you can glaze inside of it with high temperature, right? Glaze, of course, is very, very impermeable.
There are a lot of sulfates on Mars, and some Australian mines with areas with sulfates, which are also rich in sulfate in Western Australia, use plaster of Paris to build underground supports. And of course, it can be very readily dehydrated at low temperatures. You provide the own water for rehydration. And is this something that you've looked at for potentially Martian equivalents, that you'd use plaster of Paris or an equivalent dehydrated, then rehydrated sulfate as a binder?
Well, that's a great idea. We have to talk. I haven't considered that. Let's talk about it.
Have there been any calculations on power consumption for this process? I don't think this is working well. Has anyone looked at, can I achieve this with solar power?
Yeah, again, regardless of how much power you have, you can concentrate power, and if you're willing to go slowly, then of course you can always melt anything.
But especially for terrestrial use.
Oh, for terrestrial use.
A lot of the time we're not happy going very slowly.
Yeah, but you know, our early experiments were done with Fresnel lenses. So I just ordered a few Fresnel lenses, like 1 square meter in diameter. We melted a lot of material, a lot of sand, beach sand. If you go to YouTube, you'll see a video by some guy who has this machine. A 3D printer actually takes it to the moon, or to the desert, and melts the sand using Fresnel lenses.
You mentioned briefly that laser sintering with lunar regolith is not working well. Can you elaborate on it?
I did not say that. I know that in Washington State University they have done that. Yeah, so laser melts regularly too, you know. People have done this with ceramics here in the 3D printing industry. So lunar soil is just ceramics, you know, full of metal oxides, you know, different kinds of ceramics. But we have, those are for small objects. It's really impractical to use a laser to build large 3D objects like these. Any approach that requires layering of powder, like the Z-Corp, like the MIT's 3D printing, the original 3D printing method, which is powder-based, or SLS, selective laser sintering, which is powder-based. These things really are not good for large-scale printing because you have to handle a lot of powder. In the end, your structure is going to be hidden inside the powder that you piled up. Next, you have to automatically get rid of the powder outside, and worse than that, you have to get rid of the powder inside. So how is that going to be done all automatically, right? The nice thing about contour crafting is that it's pretty clean. You know, you just add whatever you need where you need it. For small scale objects, which I think are very important to be able to build out there, there are other technologies that we are working on. You know, developed another technology, SIS, selected individual sintering, that we are using for building smaller objects. Like if you want to do mining on the moon, you know, a lot of these, maybe you want to take servo motors or electronic controllers and stuff, but that you want to make the major structural members of this heavy equipment right there with the material that is there. So for those, these other technologies are good.